All right. I'm going to have to record this after school. I know somebody's going to be listening to us. All right, so f at 4. F at 4 is going to be our y2, our second differential estimate. Now, y2 is the previous y plus the rate of change at the point 2, 0 now, the new point, times another delta x of 2. The previous y we left off at was still 0, but now we expect a slope of not 0 anymore, but 2x at 2 is 4. At that point, once I get to x equal 2, I would expect the curve to slope at up 4 over 1 for 2 units in x, which would mean y would change by 8. You follow? Now, if I then say when x goes to 4, y will go to 8, then it does a little better job of estimating y, the true y, at 4. You follow?
So that between f and 4 and y2, should that be the approximation sign?
This should be an approximation. This is equal. F of 4 is approximated by it, but these y's, they stand for the actual differentials, not for the actual true value. So y represents your differential, is your differential work. Somebody asked about that in the last class, and that's good that you're paying that much attention. It is hard equal, okay? All right, now, that's great, but even going from 0 to 2 was a bit of a leap because the slope changed between there. We could get an even better estimate if instead of doing 2 steps, we did, the last class said 3. Now, 3 is logical, but what's bad about 3 steps? What's your delta x is now 4/3. That nobody gives that. Okay, so instead, let's go skip to 4 steps. Okay, if we go in 4 steps, we're trying to go from x equal 0 to x equal 4 in 4 steps. Let's first establish our delta. What's delta x? 1 unit. All right. If we go 4 units in 4 steps, we're going to go 1 unit each time. That's the first thing you're going to do is find your delta. All right. Now, if x initial is 0, y initial is 0, then let's go to our next x. The first x we come to in our movement is 1. And the y we would get is equal to the original y plus the rate of change at the previous point 0, 0 times the amount of change of x of, in this case, now 1 unit, right? What is the previous y? 0. What is the derivative at 0, 0? What was the slope at 0, 0? 0, which takes me exactly 1 unit over. So make a little segment to 1, 0. Because right now, we're at the point 1, 0. Now my second x is 2. And y2 is y1 plus a new rate of change at 1, 0 times a delta x of 1. What's the y1? Well, what y did we leave off at? 0. And what's the new slope at the point 1, 0? dy dx at 1, 0 is 2. All right. So we're expecting y to change or go up by 2 units in that next movement. Draw a little segment from 1, 0 to 2, 2. We're leaving off at the point 2, 2. It's nice work to chart the points as you go. It'll be helpful. You'll see in a second. x3. What's x3? 3. Never mind. Good job. Way to go, B. Okay, y3 then is the previous y, y2, plus the rate of change at what point? 2, 2 at the previous point times the delta x of 1. y2 left off at 2. The new slope, which is double the x coordinate, is now 4, which takes me up to the 0.36. X4 is 4, Y4 is Y3 plus dy dx at the point 36 times the delta x of 1. The y we left off at, y3, is 6. Our new rate of change is the derivative 2x at the previous point, 36, which is 6. That takes me up to 12. Now we're starting to get a heck of a lot closer to where we would expect, which is 16. And we could get better and better by doing more iterations or smaller delta x's. Now, isn't it cool how this calculus, I mean, it's different every day, but it's always the same calculus. Aren't we going smaller deltas and more iterations to get more precision? Do we do that ever? Yeah, kind of all the time. I mean, anytime we integrate, that's the infinite sum of infinitely thin. When we find arc length, we did infinitely small, infinitely many segments. Calculus is just amazing, man. Okay, so the repeated estimation in steps is Euler's method. So a logical question there would be, well, okay, that's great, but why get 12 when I can get 16, which is exact? Why go through all this mumbo jumbo when it's easier to just straight up integrate and find it at 4? So why Euler's method? And not everything can be integrated. It's usually used for non-separable differential equations, which is to say, no matter what you do, you're not going to get y's on one side, x's. It just can't be done. It can't be done. Okay? So it's a non-integrable problem that this is typically used for. Now, that's not to say sometimes we'll do easy ones that you could integrate because you want to learn on easy ones sometimes. But usually this is used on non-separable differential equations. And you'll definitely use this in diffie-q. So the idea goes like this. If you assume the derivative, or y prime, is some function. Now, students in the last class had a problem with that, why I wasn't using f prime. I guess you could, but my point is the derivative could be a function of x or y. We sometimes see the derivative as a function of x. We sometimes see the derivative as a function of y, like the exponential growth equation. Sometimes we see x's and y's. And so the derivative can depend on x or y or both. But the idea is that the estimate of a new y is the previous y plus the rate of change. This is the derivative times the amount of change in x. The more steps you do, the more precision. This, I gave you kind of ugly numbers. I think I intended for this to be 0, 1. So let's show what this looks like. And I just showed you what I want the work to look like, but we'll do it again just to make sure that you understand what I want to see and what AP would want to see. So the idea here is you're trying to estimate what this curve would be at x equal 4. What's the y when x equals 4, given that you're starting from that point, all right? And this surely matters. First, find the delta. Delta x is the difference between the x's. X, I should say, let's call it x final versus x initial in the number of steps. So in this case, we're going from an x of 0 to an x of 4 in 2 steps. And so the delta x is 2. That then tells me that if the x initial is 0, then x1 is 2 and x2 is 4, our destination. All right. Now, I didn't leave myself any room for the initial because you don't need any. It's given. X initial is 0, y initial is 1. You do need room for the previous or the subsequent y's. Y1 is I require you to give me generic formulas first and then get into the specifics. So I want y original plus the derivative, and you can name me the exact point. At which point will you find the derivative first? 0, 1, the point we were starting from, times the delta x of 2, actually you could put a delta, sorry, I should say delta x. I said general and then I went specific, sorry, delta x, right? All right, then go specific. Y initial is 1. The derivative, depending on the problem, you might sometimes have to show some work and sometimes not. However much you can do mentally. What is 2 times 0 minus 1 for the slope? Negative 1, and delta x is 2. Evaluate it as quickly as you want, but what do we got there? 1 minus 2, so negative 1. All right. The point then I am at so far is 2, negative 1. That's x1, y1. Now let's go to x2, y2. y2 is y1 plus the derivative at the previous point, 2, negative 1. That's partially why you write it out there, so it can be easily located. And the delta x is still x. Details, y1, or the y at which we left off, is negative 1. The slope is 2 times the x of 2 minus negative 1, so plus 1, times the delta x of 2. So what do you get there for your y2? 9. All right. Now you could either say y2 is 9, but preferably you would say, oh, this is kind of funky. I called this y instead of f of x, but y at 4 is approximately 9. I wish I would have, usually it's called a function. Sorry, that was dumb on me. All right. Try one on your own, please. Try this set. There are a lot of times in math where, besides an estimation method, you have a companion error bound to go with it, like trapezoid error bound. It tells you how many trapezoids you need to get precision. As far as I know, Euler's method doesn't have an error bound formula, although that would be worth looking up. I guess I should look into that. That'd be cool if it told you how many steps you need to get a certain degree of accuracy. If you're getting something big and negative and ugly, then you're on the right track. So 13 times 4, sorry, I'm slow. 13 times negative 9, so that's 90 and 27, negative 117. 2 minus 468, so negative 455. Yay? Okay. Okay, okay. Good stuff. And then, do we have time to, yeah. All right. So this is what a AP question looks like. They would involve Euler's method. How much homework questions do you have? A lot or not so much? Just one or two?
Oh,
Okay.
more than two. More than two.
All right.
Way
Maybe-
more than
some people say two, some people say
20 and 30.
maybe we should do this as a warm-up tomorrow.
Yeah.
That's a work.
All right, I don't actually remember what, that way I could get the rubric. So we'll do this tomorrow as a warm-up, that way I can dig up the rubric and you can see if you could drop a 9 on this. Let's, yeah. Okay, so let's go to these bad boys. Here we go. So, did you compare this to 1 over n and find that it diverged? Yes? Obviously, it requires more work than that, but you get the idea. This is like n over n to the 7 halves, which is 1 over n to the 5 halves. So that's what I compared to. That then converged, yay? All right, this one was a bit of a humdinger. What did you compare it to? All right. 5n over e to the n is good. The negative doesn't matter either way if you included it or not because you throw absolute value in the LCT. Now that said, once you decide those are linked, then you still have to prove that 5n over e to the n converges because that's not a layup, right? So that's actually two problems. That's a problem within a problem. Do you want to see the details to that? Or okay. So first of all, do you understand why I chose that? Those are the dominant terms in the top and the bottom. Okay, this is great, but E dominant. So E is the one you want to compare to, right? So if I do the limit comparison test to that carefully so you don't mess up the limit as n goes to infinity of 5n minus 3, I'm going to put that over 5n, and e to the n would come up here, and it would be n squared minus e to the n plus 5. Just a little gymnastics with those and switchy with me. All right, what does 5n minus 3 over 5n approach? What's 5 trillion minus 3 over 5 trillion? Pretty much just 1. So that's 1. And this, although n squared is nice and 5, those are great, and not to ignore them, but really, when n gets infinitely large, it's really about those two. It starts to approach e to the n over negative e to the n, and so that approaches negative 1, but the absolute value takes care of it. And so, at the end of the day, this limit is 1. All right, now that, from the LCT big idea, that implies that there's some harmony between the two series. The terms start to approach, as they get infinitely large, pretty much a one-to-one relationship. And so adding them should be roughly the same result. Both, because that limit is finite, not 0, both converge or both diverge. Great. Now, the question becomes, does 5n over e to the n converge or diverge? What test do you want to run to determine that? Ratio test. Wonderful. So if you run the ratio test on that by ratio test, I guess that's not a very good abbreviation. That can still be retest, but I just said it. So by the ratio test, this comes out to something like 5 times n plus 1 in parentheses over e to the n plus 1 over 5n over e to the n. Are we? That is the limit as n goes to infinity of 5n plus 5. I'll put that over 5n and e to the n over e to the n e to the first if I break up the e to the n plus 1. Wait. All right, 5 billion and 5 over 5 billion is pretty much just 1 e to the n slash, and so what's the limit? 1 over e. That's 1 over 2-ish, which is most definitely 3-ish, which is most definitely less than 1. So that implies that the series 5n over e to the n converges. Now we have established that by the limit comparison test, both converge or both diverge. 5n over e to the n converges. From those two pieces of logic, we conclude the one they give me must converge also. Or just must converge. You follow? Wasn't that fun? All right. Are we good? What about 4? Was it, I assume you compared to 1 over 2 to the n, which converges by geometric ideas? Okay. 5, I went p series on that boy, and it diverged because p is a half, which is less than 1 or equal to 1. 6, I went geometric. The common ratio is, or the absolute value of the common ratio is 1/5, which is less than 1. 7 and 8. Now that one, you had to do a little bit of strategy. They both scream comparison test, right? So which one should you choose first, the direct comparison test or the limit comparison? You should definitely figure out which one is a good direct comparison test problem first, because LCT works all the time. It's the direct comparison that has to be just right. So first of all, I didn't even want to go here, but I think this one fails direct comparison test if I design this problem correctly. So you had to do 7 by direct comparison test, and so you use the LCT for 8. Here you compared to 1 over 3 to the n, and you had to prove that series they gave you was less than converging, so converging. And the limit comparison test was against 1 over n squared, or 1 over 3n squared if you like. But the limit is finite, not 0, and so they both converged. P series p equal to greater than 1, right? Right. Okay. I went divergence theorem on 9 because the terms did not go to 0. The limit of the terms was 1/2. 10 was telescoping. I didn't write the formula for the partial sums. Let me know if you want me to. 11, I'm going to have to do a little bit of note correcting on the integral test. I went to make your test yesterday, and does anybody not take my test? That free response I gave you to the last one, where in part C they had you do this integral of a partial fraction, right? And then D was the same series, right? Are you with me? Do you remember that? Okay. Now, you would be astonished, despite the fact you just did the integral in C, how many people did not use the integral test for D? I just thought that was an assumption that everybody would go integral. Because no, I'm going to go telescoping. Yeah, no, those did not collapse. You could telescope all day long, that never collapses on itself. Sorry, no dice. So I was a little bummed there. Now, that said, the integral test was the thing, but I stripped off actually one of the points of that test. The question said, show if it converges or diverges and show the conditions of that test have been met. Now, I failed to teach you that the integral test actually has 3 conditions, positive, decreasing, and continuous. I need to add that to your notes tomorrow. So make sure you bring your integral test notes tomorrow because I need to make an adjustment. I don't want you to be lacking anything. I just blew it, I guess. I don't know. So back to this then, integral test, that proves convergence. That was also divergence theorem failure, diverges. And this went well with the ratio test because it had exponentials and factorial. It converged. The limit was less than 1. And this was a root test, and it also converged via the root test. At least that's how I did it. Okay, you follow? Those are my polar areas. Most people said, oh, I got 1, or oh, I got 2, but I didn't hear a lot of, oh, I got 3. But that's fifth period. This period is vastly superior, am I right? And so you got all 3 of those right? Right, Kendall? Good. What? Second one? Negative area is bad.
No, it wasn't.
Oh, I thought you said you got negative area. What'd you got? Oh. What did you do? So did you get 0.464 for an intersection?
Yeah,
Okay.
I figured it out.
Okay, cool. Some people did sine and cosine over the wrong intervals. Okay, let me know if you want to talk about any of those, and then, was there something else after that? I thought there was something at the bottom of it.
Yeah, there's like 3. There's a question about
Oh,
neighbors.
estimate or underestimate. Okay, so, doggone it. So, estimating an integral. How exactly did I word the question? This estimate is more than the true value. Okay, so there are 3 overestimate conclusions. You could say your estimate is more than the true value because we used blank on a blank function. Okay, so one possibility is you could get an overestimate because on this function you used, oh, trapezoids, okay. So on this function you use trapezoids. We use trapezoids sometimes to estimate. What makes for an over or underestimate if you use trapezoids? Concavity. It's all about concavity because we used, so you could, one sentence could be we use traps on a concave up curve. Okay? What's another case where you could get an overestimate of area under the curve? If on an increasing function you used right hand, okay? On the right hand, does it matter about the concavity? Look at here. This is increasing concave down up. This is increasing concave down. Does it matter concavity when you talk right hand? Not one bit. And yet, many people on the test yesterday said, oh, it's an overestimate because it's left-hand rectangles on a decreasing concave up curve. Well, the minute you put concavity in there, you lost every point you wanted. Concavity has nothing to do with it, 0. If you put it in there, you're out. Okay? So it is because you used right-hand rectangles on an increasing function, or if something was decreasing, then isn't the left side greater? Who cares if it's concave up or concave down? So you would also get an overestimate if you use left hand on a decrease. All of those are overestimations. Okay? Cool. When does a tangent line overestimate? If the curve is concave down, and does increasing or decreasing matter on over underestimate by tangent? Here's concave down, here's concave up, and that's what it's all about. It doesn't matter if it's increasing or decreasing. It's all about concavity for tangent. Okay, that's it. Is there any problem on how much you'd like to get more detail on? 18. 18? Oh, this guy. Okay, got you. Okay. So here we go. R equals 3. And 6 cosine of 4 theta is a rose with 4 petals or 8 petals? 8 petals, okay? So it goes something like, this, I believe. Nope, it goes this way. changes 225 degrees every time. So. Darn it, I missed somewhere. I screwed something up, but you get the idea. Okay. What is it? Inside both, yeah? Oh, shucks. Oh, yeah. There you go. Okay. My bad. Okay, so inside both. So these dots would be inside both. So it feels like I'm getting two regions there. That region is rose, but this region is circle, yeah? And that's actually 1/2 of one petal. So I could take that area and multiply it by 16. All right, so here we go. 16 divided by 2 times the sum of two areas. The first area is inside the circle, so it's 3 squared. Check that you remember the square. And it starts at 0 and ends when those meet. 3 equals 6 cosine of 4 theta. When cosine equals 1/2, that means 4 theta needs to equal pi over 3. So I believe that would be a pi over 12. Okay? All right. Then the next region picks up at that pi over 12 and ends when the rose gets to the origin. And so when 6 cosine of 4 theta hits the origin is when you're taking the cosine of pi over 2. So it feels like it should end at pi over 8. Oh, so does that make sense?
No, I got all this stuff.
Oh.
I am confusion why I did not get the right
Oh, so
calculator answer.
maybe you put it in the calculator? Unless maybe I put it in the calculator.
116.
That seems.
No,
like
Isaac leads on board with all these answers, so
Yeah.
Okay, so here, can I give you, this actually leads me to something here. You know that 100, first of all, common sense tells you 116, but look at, I mean, if you just looked at this whole box, isn't it at most, I mean, there's no way it's more than 36. I mean, if I enclosed in that box, I mean, not just boxing gives you an example, an idea of how to rule out multiple choices. So yeah, okay.
Should be
17,
17.
okay. 10 sine theta is diameter of 10. 2 plus 2 cosine is 4.
I don't know what it says.
2. Okay. So inside the red, but outside the sinusoid or the so it feels like I didn't draw very good focus. So it feels like it's always outer circle and inner limacon. So I think one integral, no symmetry. So from 0 to, no, not 0, sorry. That point is your starting point. So when 10 sine theta equals 2 plus 2 cosine theta is your starting point. That's theta 1.
Let's put that day.
And you went to pi?
That's pi over 2.
No.
Oh, I should go to pi.
Yeah.
Oops.
Yeah. Have a nice day. Kira. Not, what's your name?
I already signed her up. I just got home.
Gotcha. Are you allowed to sign other people up?
Yep.
You're allowed, or it just happens?
There's no rule. Yeah.
There's not?
not that I've ever heard.
Hear what you want to hear. All right. Did that come out okay? Have a great day. Sorry, whoever's listening at home. I kind of forgot to record the first couple minutes.
Piracy is not a victimless crime, I said.
Okay, so here's the start of the notes. Maybe I should just re-record.
Did you know that piracy is not a victimless
Yes, I've seen the movie before, Nick.
No, I'm talking about
So there's the notes for this page. This is really where we started to nail it all together. It's repeated differential equation estimates.
I wonder why.
Sorry, I can't remember when I started recording.
do like strange, gory sentences for the vocab. You just like
That's what the work should look like.
it's just like
Have a good day.
I miss your sentences. And I was like, you miss